So, in the previous lecture, we have introduced various types of functions of real variables and an important result, namely the Weierstrass theorem on the bound of the functions f x. In continuation, we have also discussed the Cauchy's definition of continuity of the functions. In this lecture, we will introduce the Heine's definitions of continuity of the function, and then we will establish the equivalence relation between these two definitions of continuity. We can say an important note, we can say the function f x, the function f x is continuous at a point function f x is continuous at a point if a neighborhood of the point can be determined in which the fluctuation is as small as we please, So, this is also considered as a necessary condition, because if this does not satisfy, the function cannot be continuous function. For example, suppose I take this graph, say this is our graph, point x naught is here, function f is this. Now, however small with this given epsilon, say with this given epsilon, I take this point is say f x naught. So, this point is f x naught minus epsilon, this point will be f x naught plus epsilon, and here this is f x naught. So, for this epsilon, this is the width 2 epsilon. For a given epsilon, if we get, there must exist an interval neighborhood around the point x naught such that the fluctuation should not exceed by epsilon. But what happen if it suppose I take this neighborhood, okay, this is our neighborhood like this. So, as soon as you take this point, say here, this is point here, as soon as this point, the corresponding image of this will go here. It means the fluctuation may exceed by 2 epsilon. So, it cannot be made as small as we please, and this is because there is no continuity of the curve at this point x naught. So, such a function will not be considered as a continuous function. So, that is important, that is why we say this is a case of discontinuity, continuous function, case of discontinuity, okay, because of this thing. Clear? So, that is why it is necessary condition. Now, as a corollary of this, of course, we further extend this. Suppose a function is given over a closed interval, the domain of definition is closed interval, and when we say the function is continuous over the closed interval, then what we do? We take the open interval first, and then at the point a and b also we test it. But before a the function may not be defined, after b the function may also not be defined. So, we have to modify our definition of the continuity at the end point of the interval. So, we say the function is said to be f x is said to be continuous on the right at x naught. Suppose this is x naught, on the right means this side Okay, on from the right hand side, this is right. On the right of x naught, right on the right at x naught, on a function is said to be continuous, right, if the fluctuation of the function, in a neighborhood of x naught, if the fluctuation of the function in a neighborhood of x naught on the right, that is x naught plus delta, this is a neighborhood on the right of this. If the fluctuation of the function in the neighborhood of x naught on the right of x naught on the right is as small as we please, then we say the function is continuous at a point x naught from the right hand side. Similarly, the function is said to be continuous on the left. The function f x is said to be continuous on the left of x naught if the fluctuation of the function in a neighborhood of x naught on the left means that is x naught minus delta x naught on the left is as small as we please. So, that is the important one. Okay. Yeah. So, now we can define the function over the continuity in the interval. So, we define as a continuity of the function, continuity in the interval. The function f x defined for a continuous interval a b. Continuous interval a b is said to be continuous in the interval a b, in that interval a b, that is at each point. If it is continuous at every point of the interval. Okay. If it is a closed, similarly we say f x is continuous in the closed interval or over the closed interval a b, if it is continuous at every point of the open interval a b, and continuous and continuous on the right at x equal to a and continuous on the left at x equal to b. Then we say the function is continuous. Okay. Now, let us take an example which is using the epsilon delta definition. Suppose prove that f x equal to sin x is continuous function, is continuous say over the interval 0 to pi by 2. In fact, it is continuous everywhere because it is a periodic function. So, we can say it okay, say 0 to pi by 2 is continuous. In fact, it is continuous over the entire real line R, over the entire real line R. So, the proof is simple. Suppose epsilon r is given greater than 0 is given. Okay. We have to identify delta depends on epsilon. So, that the mode of f x minus f x naught less than epsilon is less than epsilon provided x minus x naught less than delta. So, consider this, consider mode of f x minus f x naught, where let x naught be a point in this interval suppose. Okay, or all. Then what is this? This is sin x minus sin x naught, but this is equal to 2 times sin x plus x naught by 2 into sin x minus x naught by 2 mode of this, which is less than equal to. Now, sin of this thing is a bounded function bounded by 1. So, this is less than equal to 1 and this sin will be less than equal to mod x minus x naught. Why? Because mode of sin, because the sin x is less than equal to x for x lying between 0 and pi by 2. Sin 0 is 0, sin 90 is pi by 2, or even 0 to pi it will help. Okay, so, any interval you can just say this is. In fact, this can be extended for any x real x. Okay, so, this is 2. Now, if I take the f delta, so I choose delta equal to epsilon. So, if this is less than delta, obviously this will less than epsilon. So, this shows that sin x is continuous at x naught, but x naught is an arbitrary. So, it is continuous everywhere, and even if we take interval sin x is basically is continuous over any open interval a b or in the real line. In fact, this one can prove easily. So, this is one of the example which I have chosen. Now, corollary, there is one small result which we call the corollary. If f x is continuous, if f x is continuous at a point x naught and f x naught is positive, then f x is positive over the entire interval x naught minus x naught plus delta. Means if the function is continuous at point and at the point x naught it is positive function, it is a positive function, graph is up, then we can find a neighborhood where the function will remain positive. Okay. The reason is because it is continuous. So, this condition is satisfied for a given epsilon greater than 0. There exists a delta depending on epsilon such that this is true provided mod of x minus x naught less than delta. So, when the x lies between this, then what happen? This shows the f x is lying between f x naught plus epsilon greater than f x naught minus epsilon. So, if I choose epsilon to be half of f x naught, then obviously f x will always be greater than will be basically half of f x naught. because of the left hand side which is positive. So, this is true for all x belongs to the neighborhood of x naught, neighborhood of x naught with the radius delta. Okay. So, this now Heine definition for n, definition of continuity given by Heine. This is given in terms of the sequence. So, what he says, let x1, x2, xn, x1, x2, xn be a convergent sequence of real numbers, say of real numbers or points on the real line in the given interval a b, in the given interval whose limit is say a, limit is say a. The function f x, by definition of the function f x is said to be continuous, at a point a if for every such sequence, for every such convergent sequences xn, every such convergent sequence xn, the sequence of their functionals value, sequence of numbers, functional value means it is in numbers now, f of xn, this is real numbers, converges to f of a. That is, the meaning is f is continuous at a point x equal to say x equal to a if the limit of the function f x when x tends to a exist and coincide with the functional value at a. This definition is if and only if. In fact, this is the definition given by this. It's okay if this condition. Okay. In fact, it's part if and only if also function b. So, what it says is that if we take a sequence xn which converges to a, then f of xn will go to f a. That is the definition given by the Heine. Now, these two definitions are basically equivalent definition. The equivalence of Cauchy's and Heine's definition of continuity. So, let us assume the function is continuous. Assume f x is continuous in according to Cauchy's. It means that is for a given epsilon greater than 0, there exists a delta depending on epsilon such that mod of f x minus f x naught continuous at x naught. F x naught is less than epsilon provided mod of x minus x naught less than delta. Suppose this is true. Okay. Now, let us consider a sequence xn, a convergent sequence xn having the limit a, means xn sequence converges to a. So, by definition, modulus of xn minus a is less than say delta for all n greater than equal to say capital small m, say, because limit of xn is a. So, xn minus a will remain less than after a certain stage. But if xn lies itna, this implies that xn lies between a minus delta and a plus delta for all n greater than equal to m. And for such point which lies in this one satisfy this condition, So, using one, what we get is mod of f x n minus f x naught, yes, continuous at x naught. So, here x naught, actually I have taken a limit is x naught, let us take x naught here. So, x naught. So, here is x naught, this is also x naught, because in place of this. So, f x naught, this will remain less than epsilon r for all n greater than equal to m. Therefore, limit of f x n as n tends to infinity is f x naught. Hence, Heine's definition follows. Hence, by Heine's definition, f is continuous at x naught. Conversely, suppose Heine definition, suppose f is continuous at x naught in accordance to Heine's definition. Suppose this. Suppose we say it's continuous in accordance with, but Cauchy's definition is not. Cauchy's definition is not satisfied. That is, for a given epsilon r greater than 0, for a given epsilon r greater than 0, there exist points, in the interval, say x naught minus delta, x naught plus delta, for which the fluctuation mod of f x minus f x naught exceed by any given number epsilon, howsoever small delta may be. So, what do you mean by this? This means, if you take a sequence which is in this, okay, then all these sequence, so let us take a consider a sequence delta n of decreasing nature, which decreases to 0, converges to 0, such that sequence delta n will converge to 0, such that, and x n be a point belongs to this x naught minus delta n, x naught plus delta n. If we take this point in this sequence of the point in this interval, then according to the second implies that mod of f x n minus f x naught will greater than equal to epsilon. This shows the limit of the f x n as n tends to infinity, as x tends to x naught, that is n tends to infinity means x n tends to infinity is not equal to f x naught. So, function f is not continuous at x naught. All is contradicts the definition of this. Therefore, this assumption that Cauchy definition is not very satisfied is wrong. Therefore, okay. Thank you very much. So, this was the equivalence of this.